Thank you, everybody, for joining today's Health Ethics Institute webinar. My name is Gabriela Daza, and I'm a research assistant here at HEI. Before I turn it over to our moderator and delve into the webinar, I'd like to make a few housekeeping announcements. First, all attendees are muted for the duration of the webinar. You can turn on closed captioning at the bottom of your screen on the right of the Q&A button. We will reserve about 15 minutes at the end for a more extensive Q&A and discussion period. Please submit questions via the Q&A function at any time during the webinar. And if you experience any logistical difficulties, please also contact us using the Q&A box. HEI is a nonprofit corporation chartered in 1980 as an independent research organization that provides impartial science to inform decisions that foster a healthier environment and better health for all. Since 2022, HEI Energy's research program has supported research to improve our understanding of potential population exposures associated with unconventional oil and gas development in the United States. We've supported a total of 9 studies, 3 of which seek to assess trends in air quality and community exposures from unconventional oil and gas in regions across the United States. We also funded the Tracking Community Exposures and Releases Collaborative, TRACER, to better understand community exposures to air emissions and noise from oil and gas development in multiple US regions. There have been 2 studies on water-related exposures in Colorado and Pennsylvania, both of which explore the relationship between oil and gas development and instances of known or potential water contamination. And finally, what we will hear about today is a 3rd water-related study that built a regional groundwater model to understand well water vulnerability to contamination from spills associated with oil and gas development across the Marcellus region. Before I turn things over, I would like to acknowledge my co-organizers at HEI and thank our speakers and moderator for joining us. Now I'm very happy to introduce our moderator, Dr. George Hornberger. George Hornberger is a distinguished professor emeritus at Vanderbilt University in Nashville, Tennessee. From August 2008 to June 2021, he was the director of the Vanderbilt Institute for Energy and the Environment, with a shared appointment as the Craig E. Philip Professor of Engineering and as a professor of Earth and Environmental Sciences. His current work focuses on coupled natural human systems and aims to understand how climate, groundwater, surface water, energy production, food production, and human abstraction of water interact in complex ways. George is the chair of the HEI Energy Research Committee and has been a member since 2014. Thank you, and take it away, George.
Thank you very much, Gabriella. As you see by this slide, we're going to be entertained by Dr. James Saiers and Dr. Mario Soriano today. They have basically been working on how we can understand potential vulnerability to water contamination, groundwater contamination due to unconventional oil and gas development. They are focused very broadly across the entire Marcellus Basin, which clearly we are looking at the broad picture and not just a site-specific example. So I think what I'll do is just progress to introducing our speakers. As I said, Professor Saiers is a hydrologist at Yale University. His recent research addresses drinking water impacts of fossil fuel development, natural carbon capture and carbon cycling within watersheds, and migration of contaminants through groundwater aquifers. The research relies on both experimentation and mathematical modeling, and he collaborates very broadly with ecologists, geochemists, engineers, and epidemiologists. His overarching goal is to generate new observations and to develop predictive approaches that can be used to inform water resources management approaches. Dr. Mario Soriano is an assistant professor in the Department of Geography at the National University of Singapore. Prior to joining NUS, he was a postdoctoral research associate and environmental fellow at Princeton University. He worked on his PhD in hydrology and water resources from Yale University. His research examines the movement of water and contaminants in the environment through the robust integration of observations and high-fidelity simulation models. Dr. Soriano's interests explore the intersections of human activities and narratives that frame water as both a natural resource and a natural hazard. His experience on collaborative projects on the water energy nexus, sustainable food systems, and environmental communication. So without further ado, I will turn this over to Jim Saiers and Mariano.
Thanks very much, George. As George indicated, Mario and I are going to team up on this presentation. I'd also like to introduce our co-investigators, Josh Warren, who's a biostatistician here at Yale, and Reed Maxwell, who's a hydrologist at Princeton. I'd also like to recognize the good efforts of several undergraduate and graduate students at our universities, Shuke Lin, David Van Velden, Kathy Yang, and Katie Baker. So I'll get us started with a very quick overview of unconventional oil and gas development, and then touch briefly on some background on its intersections with drinking water quality. Unconventional oil and gas development involves the extraction of oil or natural gas from low permeability formations by a combination of hydraulic fracturing and horizontal drilling. While fracking and unconventional oil and gas development are often treated synonymously, unconventional oil and gas development actually involves several stages. After the leases are signed and permits obtained, the first step is to prepare the site. And in the Appalachian Basin where we're working, this typically involves construction of new roads and then clearing of the land surface and leveling it for the well pad. After the site has been prepared, drilling can commence. And this is often done in two stages, sometimes with two different drill rigs. In the first stage, the vertical section of the well is drilled. And this vertical section typically goes down more than a mile. And then the drill bit is turned horizontally to drill the lateral section through the Marcellus Shale. These laterals now are in some cases exceeding 2 miles in length. After the well is drilled, hydraulic fracturing can begin. And this involves injecting water with some additives and a prodigious amount of sand into the borehole under high pressures. And these high pressures overcome the tensile strength and compressive forces of the rock and the Marcellus Shale or the target formation fractures. The process from site preparation to hydraulic fracturing typically takes on the order of several weeks. After the well is completed, it can go in production, whereupon natural gas liquids, or oil may be produced along with wastewater. And this production can last many years. So public views on unconventional oil and gas development are a bit mixed. The benefits are undeniable. A recent survey showed that many respondents identified several benefits, including the role that unconventional oil and gas development can have on strengthening local and regional economies, its role in reducing energy prices, and also creating jobs. Despite these advantages, long-standing concerns regarding unconventional oil and gas development have persisted. And principal among these are the potential role that unconventional oil and gas can have in contributing to drinking water pollution that may imperil human health. These concerns are particularly salient in areas that host UOGD and also where the residents rely on domestic wells for water to support their everyday needs. This graphic here shows that in many places in the United States, unconventional oil and gas development activities occur within a kilometer of drinking water wells. And this is particularly the case in the Marcellus Shale region and the underlying Utica Shale of the northern Appalachian Basin. So I indicated there are concerns about the potential for pollution. What are the mechanisms that underlie these concerns? Well, when unconventional oil and gas development moved into the Appalachian Basin more than 2 decades ago, original concern centered around the role of fracking itself, in that the possibility that high pressures associated with fracking could lead to the movement of expulsion of fluids up into shallow drinking water aquifers. Subsequent studies have shown that the thick rock between the Marcellus Shale and the aquifer provided an effective barrier against this migration. Others propose the possibility that natural fractures created by geologic processes could short circuit fracking fluids and other chemicals up into overlying aquifers. However, there's no evidence that these fractures offer this connectivity. There are potential man-made conduits to short circuit fracking fluids and formation chemicals, and these are abandoned oil and gas wells. There have been isolated instances in which stimulation of target formations have led to the expulsion of fluids through old oil and gas wells. However, this is an uncommon occurrence, and oil and gas producers take steps to survey the area to prevent this from happening. A more likely culprit of contamination has to do with poorly constructed oil and gas wells. In the early stages of development in the Appalachian Basin, improperly cased and cemented wells had, in some instances, allowed methane to migrate along the borehole and into shallow drinking water aquifers. And this methane, natural gas, could have been derived from the Marcellus or more shallow gas-charged units. There is evidence that regulations put in place about 12 years ago that strengthened casing and cementing regulations have alleviated this problem. It's processes at the surface rather than underground that are probably a more frequent threat to impairment of shallow drinking water aquifers. Oil and gas production companies spend about as much time handling wastewater from their activities as they do pulling hydrocarbons from the ground. Sometimes this wastewater is spilled. A study conducted by Patterson suggested that 10 years following the onset of unconventional oil and gas development in Pennsylvania, there were over 1,300 spills of wastewater. These spills might contain hydraulic fracturing solution, which is largely water, but it contains additives to improve fracturing performance. It could also include spent drilling fluid, as well as flowback and produced water. These are waters that come out of the gas well. They're typically comprised of very saline formation water, together with hydrocarbons and potentially residual drilling and hydraulic fracturing solutions. These materials can be spilled inadvertently through tanks, leaking tanks and pits, through leaks and flow lines, and through accidental releases at the wellhead during fracking and drilling operations. Our research focused on the potential effects that these spills might have on drinking water quality in the Appalachian Basin. In particular, the goal of our research was to advance an approach for evaluating the vulnerability of domestic water wells to contamination from spills associated with unconventional oil and gas development. It was our intention to make this platform amenable to Marcellus-wide application. The Marcellus area covers over 300,000 square kilometers. But at the same time, we wanted to do this at high spatial resolution in recognition that issues of groundwater contamination often are quite localized. In contrast to previous proximity-based metrics for vulnerability, our approach is physically based in that it's capable of accounting for hydrologic processes that may transport spilled fluids from well pads to domestic well locations. And it was also important to tailor our modeling approach to account for various data limitations. Some of these limitations have to do with incomplete data on the characteristics of spills from well pads, as well as the sparsity of hydrogeochemical information that is often used to inform bait and transport simulation. Now I'm going to turn it over to Mario to define vulnerability and to discuss our vulnerability approach.
Yes, thanks, Jim. So our approach really operationalizes this concept of vulnerability from a hydrologic standpoint, which is based on the notion of a source pathway receptor relationship between our known oil and gas well pads and spill locations and our receptors, which are our drinking water wells. So in our framework, vulnerability is defined as the likelihood of drinking water impairment at a receptor in the event of a contaminant release from a source. And this approach requires the detailed understanding of groundwater flow paths, which we obtain by combining a physically based groundwater modeling, ensemble calibration, as well as particle tracking. The next slide. And so I'm going to briefly walk through the different stages of our analysis here for our vulnerability modeling framework. So we start with a synthesis of various geographic data sets into a common database through GIS, the Geographic Information Systems, which we use as a basis for developing our groundwater flow models. In this case, we're using the open source code ModFlow 6 to model the movement of groundwater. So this simulation gives us the distribution of groundwater levels across our study area, as you can see in the upper kind of center figure in there. And these simulations are comparable to some field observations that we also obtained from publicly accessible databases. And so we compare how our model does against these observed groundwater levels. And from there, the next stage is ensemble calibration, which I'm going to talk about more later. But briefly, this is the process by which we adjust our model parameters in order to improve the agreement between our simulations and our available observations of groundwater levels. And we can go to the next slide.
Brian, Mario.
Yeah, I'm just waiting for, okay, yes. Sorry, my internet connection may be a little bit lagging behind. Oh, goodbye. Okay, yes, this slide, thank you. So these now calibrated set of groundwater flow models are used in the subsequent stage, which is particle tracking, wherein we then simulate the movement of contaminants in our groundwater flow system through our particle tracking code, in this case, ModPath 7, that is simulating the movement of these contaminants from spills or unconventional oil and gas well pads towards discharge locations in the groundwater flow system. We integrate the results across our ensemble of models and finally calculate vulnerability, our vulnerability metric. And so our groundwater flow models are based off of this earlier published work by Zell and Sanford of the USGS, that's the US Geological Survey, who developed this set of 75 modeling domains across the contiguous United States here. And in our case, we just selected the modeling domains that corresponds to the Marcellus region as shown by the red box there. We retained from the Zell and Sanford models the model domain boundaries as well as the discretization, which is 250 meters by 250 meters, as well as the top and bottom elevations that define the model. But in our framework, we expand on this as well by testing alternative subsurface parameterizations. That is how we are defining those parameters for the geology that are important for the groundwater movement, as well as the recharge boundary conditions, which is essentially how much water is percolating downwards into our aquifer system. Next slide. So this is that zoomed in view of those modeling domains that we carry on in our analysis. So there are four modeling domains carried over from Zell and Sanford analysis here that correspond to the Marcellus region. We have the Susquehanna River Basin, so that's the domain ID 0205, as well as the Ohio, Muskingum, Kanawha, and so forth, as you can see on this table. And altogether, these account for a total study area of 305,000 square kilometers, with again the goal being to encompass the entirety of the Marcellus region here. Okay, so the next part, as I mentioned, involves the evaluation of our initial simulations against available field observations of groundwater levels. So ensemble calibration is the process of adjusting these parameters in order to maximize that agreement. So maybe just to walk through this slide a little bit. So parameters of the groundwater flow model are uncertain. And what this is saying is illustrated in the graph on the right-hand side here. You can see that for a given type of geology, whether that's your unconsolidated deposits like gravel or sand, or your rocks, there, you can see that there is a wide range of possible values for the parameter known as hydraulic conductivity, or K. So this illustrates that even if we have a pretty good idea of what the formation is in terms of its characteristic geology, the parameters can still have a wide range of possible values. And so we're able to reduce that uncertainty through the process of calibration, where we try to minimize the residuals, or that is the mismatch between our observations of water table depths and our simulated equivalents there. And because the problem is non-unique, which just means that there are many possible solutions to this type of inverse problem, we are adopting an ensemble approach where we are not just looking at one optimal solution, but instead we look at a whole universe of possible optimal parameters. And the approach there is through the PES-PPIES Gauss-Levenberg-Marquardt algorithm there. So this is just an illustration of that process. So each of these four panels corresponds to one of the modeling domains that I had mentioned earlier. And so if we just look at the top left graph there, that is for the Susquehanna River Basin. The y-axis, or the vertical axis here, represents that mismatch between our simulations and the available observations of groundwater levels. And as you can see, we had this given value at the start of our analysis, but then through the process of simulation, as we go forward along the horizontal axis here, we can see that that mismatch is indeed reduced by the process of calibration. And so that's what these plots are showing for our different modeling domains, as well as for the different alternative setups that we had tested there. Okay, next slide. And so once we have that set or that ensemble of models where we had essentially tuned the models to agree with our available observations, we then use those calibrated models for particle tracking, wherein again, this is a way of operationalizing the source pathway receptor framework. And so we initialize these particles at sources. In this case, these could be spills or unconventional oil and gas well paths, and track them forward until they exit the groundwater flow system. And so this represents the maximum advective transport distance in the groundwater system, and also represents a conservative scenario where we're not considering things like degradation or dilution of the contaminants. And really, what this amounts to is a precautionary type of analysis that is also partly due to the fact that we don't have good data on the composition of these spilled materials. And so the particles are also initialized at the top face of the grid cells to simulate spills at the surface. And again, this is implemented through ModPath 7. And so just looking at the bottom right 3 panels there, this again just illustrates the ensemble concept here, where each member of the ensemble or each realization, as you can see, you have 3 realizations being shown, R1, R2, and R1000, represents a slightly different kind of calibrated parameter set that also results in some slight differences in these delineated path lines for our particles. Okay, next slide. And so we take advantage of this fact that we are now having this ensemble of particle tracks that are slightly different from each other. And we integrate them basically by looking at the variability of those realizations at all the points in our domain. And that is then what we define as vulnerability. So vulnerability is simply calculated as the proportion of realizations where a particle track intersects a given location. And so I didn't put a legend on this rightmost panel here, but basically the red colors correspond to high vulnerability. These are the grid cells where majority of our ensemble realizations are indicating that particles are going to be expected to intersect that given location. And then the cooler blue colors here indicate that fewer realizations suggest that that location may be impacted. Okay, next slide. And so really, all right. So really we need kind of 2 sets of geolocated information for this analysis. So our first one would correspond to what our sources are. In this case, we were really interested in the spills for associated with unconventional oil and gas. So we collected these information from regulatory agencies as well as from peer-reviewed publications, specifically the Lauren Patterson 2017 paper, but you can see these differences across the 3 states that are included in our analysis. So in Pennsylvania, we have over the 1,600 spills from 2007 to 2023. And again, a large proportion of those do come from the Patterson et al. Data set. And then in Ohio and West Virginia, we have a much smaller number of spills. Although I should note that when we collated this information from the agencies, we did have much higher numbers of spills that we started with, but because of several criteria that we had implemented as well. So we had to end up with these smaller numbers. So in particular, if the records that we got did not have any information about where the spill was located or when it occurred, we had to exclude those. We also had to exclude the spills where we could not verify their location to be in the um, unconventional oil and gas locations as well. So we had to exclude those from our analysis too. Okay. Next slide. And so this is the overall result for our vulnerability analysis to those spills. You can see a zoomed in region on the upper right panel in there. So again, as I mentioned, vulnerability goes from a low value of 0 vulnerability up to a high value of 1, which would indicate that a majority of our simulations that are in the ensemble suggest that these locations would be intersected by a path line. And so we can summarize, for example, the area of grid cells that vulnerability or that exceed these different thresholds of vulnerability. So if we have this threshold of 0.001, the total area that is affected is 616 square kilometers. And going down the table here up to a threshold of 0.5, we see that we have an area of 576 square kilometers. And again, this assumes the conservative transport from spills to our discharge locations here. Okay, next slide. And so one of the interesting things that we could do as well from this analysis is to then I try to identify or map out the populations that might be potentially vulnerable as well here. So we match this with this data set from Johnson et al. This is also from the US Geological Survey data set of the population dependent on domestic groundwater in our region of interest here. And so basically, we can intersect these two georeference data sets and say, for example, that almost 25,000 people rely on domestic wells in locations where the vulnerability exceeds 0.001. And again, going down the table here, almost 22,000 people rely on domestic wells in locations where the vulnerability exceeds 0.5. And so if we look at that very at that largest number there, so almost 25,000, that is about 0.6% of the 3.9 million people relying on domestic wells within the Marcellus. And so these are, again, estimates that are based on known spills that we could positively geolocate within also known unconventional oil and gas well pads. Okay, next slide. And so really, we are sort of confident that we probably are missing quite a bit of the spills in the analysis that I had just described, right? Whether that is due to reporting limitations or possibly some gaps in monitoring or even just our some of these may not have been recorded at all. And so we were curious, so what if we just conduct an analysis where we assume that at all of the well pads, some form of spill has occurred. So that is what is being shown on the right panel here. And again, on the left panel, what's being shown is just with the spills that we know occurred at unconventional oil and gas locations. And so we can see that if we do make this assumption that all of the known well pads have had some sort of spill associated with them, then we can see a significant increase in the area that we simulate could be vulnerable to these types of events. The reality is probably somewhere in the middle, but we are also wanting to just look at the most precautionary sort of scenario here again. And go to the next slide. So finally, how this translates to the populations that are potentially vulnerable as well. We can see almost, almost an order of magnitude or increase in the populations that are affected potentially by these types of events. So if we look at the lowest threshold that we looked at, 0.001, we go from 25,000 people that are vulnerable to known spills, going up to 147,000 people vulnerable to all of the well pads that have ever been drilled in the region. Okay, and I'm going to turn it back to Jim for the rest of the webinar.
Okay, the next phase of our research, which was led by our biostatistician on the project, Josh Warren, involved examining associations between UOG fingerprints and vulnerability. And so our working assumption was that if our vulnerability approach was correctly approximating conditions that favored groundwater impairment, then we should see statistically significant associations between vulnerability and actual measurements of groundwater quality. So we use logistic regression models to quantify the relationship between our model computed vulnerability and the presence or absence of chemical fingerprints of spills in domestic well waters. So generally speaking, we used two models. One was an unadjusted model in which vulnerability from our modeling was included as a sole predictor of a binary outcome variable. And then we compared the results to an adjusted model that included other covariates to account for other factors that might influence the probability of a water sample having a chemical fingerprint of a spill. These covariates were indicators of topographic positions of the water wells in recognition that natural upwelling of deep basin brines tends to occur in valley locations, and this can impart a UOG-like signature to drinking water samples. So to do this analysis, we needed data on drinking water quality, and we didn't collect new data as a part of our study, but we relied on published observations. We leaned very heavily on Shell Network database, and this is a database managed by Tao Wen and until recently Sue Brantley. But we also relied on, to a lesser extent, peer-reviewed publications that reported water quality data. We applied our logistic regression model to water quality measurements made from 10,000 domestic wells in 9 counties of northeastern PA, what are shown in the map there up on the right. This area is characterized by a very low density of conventional oil and gas development, but quite a high density of unconventional oil and gas development. And this allows us to isolate the effects of UOGD. We process the water quality data for fingerprints of spills on the basis of ratios of inorganic ion concentrations. Ratios of inorganic ion concentrations are used widely by hydrologists and geochemists to identify sources of groundwater and surface water. In accordance with published studies, we used bivariate combinations of ion ratios, such as the one shown on the right here, to distinguish unimpacted meteoric groundwater from those groundwaters that might be affected by mixing with shale gas produced water, which comprises a large fraction of the spills in our study region. We started by considering 6 different fingerprint criteria based on different ion ratio combinations. At the outset, we had to eliminate 4 of these criteria, primarily because our data set had large numbers of missing or censored bromide and lithium measurements, or because of low classification accuracy. The 2 criteria that were standing classified 97.5% of a subset of well waters that were certainly unimpacted correctly. What do I mean by certainly unimpacted? These are well waters that were collected from wells located more than 2.5 kilometers away from documented spills. Of the remaining 2 criteria, the one that used calcium classified Marcellus produced waters considerably more accurately than the one remaining criteria that used sulfate. Therefore, we considered the criterion that used the ratios of calcium to strontium and calcium to magnesium is the most reliable criterion for distinguishing unimpacted well waters from those with chemical fingerprints of UOG spills. It's important to note here that a UOG fingerprint is not equivalent to exceedance of a health-based regulatory standard. That we used inorganic ions instead of concentrations of organic analytes that might have greater health-based relevance, such as volatile organic compounds or hydrocarbons, reflects the relative scarcity of geolocated measurements of these organic analytes, and that many of these organic analytes have multiple sources, which may be unknown and unrelated to UOGD. So here are the results of our unadjusted logistic regression model. And this model just uses vulnerability as the sole predictor of UOGD spill fingerprint detection. The odds ratio here is 1.04. Based on the way that we scaled vulnerability, this odd ratio implies that for every 5% increase in model computed vulnerability, the odds of detecting a UOG fingerprint increased by 4%. This result was statistically significant. We went on to consider our results from our adjusted logistic regression model. This model accounts for other covariates that may affect the probability of a water sample exhibiting a UOG type chemical signature. The primary result, that is, the odds ratio on vulnerability, is still statistically significant, although the effect size is slightly reduced. Specifically, according to an odds ratio of 1.03, this means that for every 5% increase in vulnerability, the odds of detecting a UOG fingerprint increase by 3%. These results then offer support for the notion that our vulnerability approach that accounts for hydrologic processes is appropriate for identifying areas that might be susceptible to contamination from spills from unconventional oil and gas development. So I think we're nearing the end of our time here, so I'll cut to our conclusions. So based on the results that Mario presented, these results suggest that a small proportion of household wells within the Marcellus region are vulnerable to contamination from present unconventional oil and gas operations. Our estimates of vulnerability are lower than those that are derived specific or significant or just solely from proximity-based metrics. And the reason for that is that these proximity metrics fail to account for the effects of groundwater flow patterns in distributing contaminants through the subsurface. On average, the proportion of vulnerable populations is low, but our results also show that the density of vulnerable wells exhibits considerable variation. And it's important to understand what this variation is. And our vulnerability approach does that. We think that going forward, our vulnerability approach could potentially be used in a number of ways. One way is to support contaminant source attribution analyses. It could help inform science-based setback distances that are intended to protect drinking water resources. And it could also optimize sampling locations for groundwater monitoring programs by prioritizing sites that are most vulnerable. We're interested in continuing this work, and there's clearly more left to do. But we think that refinement and extension of this framework will rely perhaps first and foremost on improvements in the comprehensiveness, collection, and management of records associated with fluid releases from unconventional oil and gas operations. And with that, I'll acknowledge the generous support of the Health Effects Institute.
Thank you both for a wonderful presentation. We are now going to be moving into the Q&A discussion with our speakers for the last section of this webinar. Dr. George Bornberger will be moderating this discussion, and please feel free to send any questions into the Q&A box, and we will do our best to get to them.
Great. Thank you, Gabrielle, and thank you, Jim and Mario, for such a great presentation. Very informative. So, as you noted in your presentation, your approach is conservative, I think is the term you used, in that you don't take into account processes like dispersion or adhesion or whatever. What do you think how do you interpret your results in light of this assumption?
Yes, so thanks, George, for that question. Yeah, so certainly one of our main kind of thought processes for adopting this type of approach was to make the best use of the data that we have. And in this case, one of the main challenges that we had was the lack of these detailed characterizations of the nature and composition of the spilled materials there. And so we adopted an approach that would enable us to gain still some physically based insights, kind of looking more towards the most precautionary scenario that we could anticipate based on our analysis. And so certainly if we had more detailed information, we could incorporate that type of or those types of processes in the analysis as well. Jim?
I'll follow up very quickly on that, George, in that, so if as you said, we had sort of chemical specific information and can include issues like absorption or degradation, our relatively low estimates of vulnerability would be even less.
Right.
And so that's the way we would like to move in the future, is to include that. But I think actually inclusion of that information will necessarily have to be done on sort of a site-by-site basis.
Yeah, yep, I can see that. So let me try a broader question. Okay, so you indicated, Jim, and I think your penultimate slide, that some of the ways it could be used. So your results. So how do you picture the information that you have assembled being useful to, let's say, either residents of areas who are concerned, or to, water quality scientists in the region?
So I think I can start. One of the applications that we are really hoping for this more broadly is to enhance these more targeted sampling and monitoring campaigns out in the field. And that's also recognizing sort of limited resources in terms of manpower and the equipment that we can deploy and those types of considerations. So in the event that, let's say, for example, a spill is reported at a given location, where are the areas that we can have the highest likelihood of seeing some sort of impact, and so we can sort of target our monitoring towards those locations.
Yeah, it didn't talk about it too much, but in certain areas of the Appalachian Basin, there's a legacy of extractive industry. It's just not unconventional oil and gas development, it's conventional oil and gas development, coal mining. And one of the ways that this sort of approach could be used is to help distinguish, in cases of concerns about water quality, likely sources of impairment. You can imagine it would be nice where you could have a dashboard that would be publicly available and it would show sort of vulnerability. There would have to be a lot of text that goes with that. We did the best we could in terms of our estimates, and to account for uncertainty, but it's still uncertain. But that information, together with encouraging people who might be concerned about their water quality, to spend some money and test their drinking water, I think could be useful.
Good. So we had a question posted. How did you have surface spills? Is there any concern for surface runoff that you considered? And also, did you consider the unsaturated zone?
Yes, that's a great question. So in the mod flow analysis that we presented in here, that does sort of assume negligible effect of the vadose zone. Although we did test out some integrated modeling approaches as well, where we considered both surface water and the unsaturated zone as well as the saturated zone in our analysis. And basically, what that work showed was that the greatest transports happen, of course, probably that we might expect in the saturated zone, and when there's very limited kind of lateral transport in the unsaturated zone as well. The computational effort for that was not tractable to apply on this regional sort of scale analysis. That was the other goal of our project. But yes, we did look at those in a kind of more targeted manner.
Right. Probably a quick clarification question. When we use particle transport, to clarify, this is not necessarily a physical particle that you're modeling. So whereas, the normal use of particle would picture something that is actually a particle being modeled.
Yeah, so that those particles, they're definitely virtual, and what they're doing is they're tracing the direction that dissolved contaminants would travel as they move with groundwater. And because we run many realizations, we get slightly different trajectories depending on the way the groundwater model is parameterized. And that those many realizations are intended to account for uncertainty in those flow paths.
Okay, so we have a question that was put in the chat, and that was similar to a question that I had, and that part of it is there's a time estimate too in terms of transport, and so if you have somebody, let's say, who lives 1,700 feet away from a UOG well, and they look at your results, how do they judge whether they, first of all, should have their well tested? And second of all, is there a time aspect? And then finally, what should they have it tested for?
Do you want me to start on that one, Mario?
Yes, I think, yeah.
Okay, so just to give some background that is probably broader than what you're expecting, is that the travel times depend on sort of the distance from the source, the well pads, to the receptor, drinking water well. Also depend on local hydrologic conditions that affect groundwater flow paths and groundwater flow rates. Our vulnerability analysis, our particle tracking analysis, allows us to estimate, for example, arrival times at receptor locations. We didn't show any of that. It's quite varied. One of the analysis that we've done in the past is, for example, we looked at Pennsylvania setback distances, 152 meters, okay? And then we looked across our region, how long would it take spilled solutes to travel that distance, okay, given these local variations in hydrology that vary from one location to the next. And that variation in travel times to that setback distance of 152 meters is great. It can vary from hundreds of years, all right, to months. And so that's where, and that depends on the hydraulic connectivity and flow paths. The median travel time in that case was 3 years, right? Fast flow paths, we're getting there. The 90th percentile flow paths, that was on the order of months. And so visual display is not amenable to that. And so you have to sort of drill down into the results. And just one more thing there is, we can model that. Our model gives us travel times. But those model travel times also depend on porosity, which, unlike hydraulic connectivity, for example, we cannot constrain as well. So that's kind of the ugly parts that
No, that's good. I realize that it's a difficult issue. So we've actually, I think, come to the end of our time, and I am going to turn it back to Gabriella, who has some final comments. Thank you very much again, both Jim and Mario.
Thanks, George.
Okay, thank you. So I just have some wrap-up items right now. First of all, thank you to everyone who asked questions, and thank you again to our speakers for, let me put this in presenter mode. For your responses and for this wonderful presentation. I'd like to quickly share what's next for HEI Energy. The recording for this webinar will be posted to our website in the coming weeks. Additionally, final reports for our studies will be live on our website in the coming months. And in the meanwhile, you can sign up for updates. And again, thank you so much to all of our attendees, our speakers, and our moderator. And please complete the feedback survey that I put in the chat. There will be a second chance to do so in the follow-up email that we're sending later on. We appreciate your feedback so much and thank you for joining.